Hello everybody. In this video, I want to talk a little bit about concentrations. And for many of you, especially those in like the medical field or interested in the medical field, this is really going to be the most important thing for you to take away from this course. And the reason for that is, and the reason that chemists are really interested in solutions in the first place, is because it allows us to deliver a specific amount of mass or moles of something by making measurements of volume, which is typically a lot easier than, say, weighing something out and doing some calculations and stuff. We want to know what is the proper volume to deliver. You'll see this often when you're delivering any kind of medication in a liquid form or something like that. There's a certain amount of that medication that is in a certain amount of volume, and you need to be able to manipulate that in order to deliver the correct amount. So what is concentration? It is the amount of solute present in a particular volume or mass of a solution. There are many different concentration units, and each is appropriate for different kinds of circumstances. So you're going to see different units used depending on what kind of field you go into. One of them that is pretty common is what we call the mass percentage. We often abbreviate this as mass with a percent symbol here. And this is going to equal the mass of the solute divided by the mass of the solution, where the mass of the solution is the mass of the solute plus the mass of the solvent. And that is important that we learn to make a distinction between solution and solvent. While it's often true that when there's much more solvent than solute, that the mass of the solvent is equal to the mass of the solution, it is often not the case that that's true, and we need to account for the mass of the solute when we consider the mass of the solution. Another unit that we're going to see often is going to be our volume percentage. Again, we abbreviate this with volume as a percent and then a percent symbol. And this is going to equal the volume of the solute divided by the volume of the solution, where for our homework problems, we're going to call the volume of the solution equal to the volume of the solvent plus the volume of the solute plus the volume of the solvent. But this isn't really actually true, which is why I really don't like to use this unit in general. It is entirely possible that when you add the solute to the solvent to form a solution, the density of that solution changes. And it's not simply an average between the density of the solute and the solvent, but instead the interactions are sufficiently different that we get a different density, and this volume of the solution is going to change. One of the classic examples of this is like ethanol and water. And so like people who are making like distilled spirits and stuff, they're very aware of the fact that if you mix a liter of pure ethanol and a liter of pure water, you're actually going to get 1.8 liters of solution, which is a loss of 10%, which could be significant to their bottom line. So this just generally isn't true, but we're going to assume that it is for your guys' homework. The next one that we're going to talk about is going to be our mass volume percentage. We can abbreviate it like this, and that's going to be the mass of our solute divided by the volume of the solution. Again, we're going to times that by 100%. This is also kind of a problematic unit for the same sort of reasons, but it is true that when we have the volume of the solution, when we're dealing with mostly water, it has a density very near 1. and the mass volume percentage is really, really close to the mass percentage if we have a sufficient amount of water in our solution. So mass percent, volume percent, and mass volume percent all deal with volume and mass, but most often when we're doing chemistry, we actually care more about the number of moles of solute that we're able to deliver. And so we have a set of important concentration units that we tend to use a little bit more than those other ones. The most ubiquitous one, the one that you're going to see the most often, is molarity. And this is going to be the moles of solute divided by the liters of solution. Note that here we're actually specifying the exact amount of volume, where before we were just dividing by pretty much any volume unit, or milliliters most often, but you could formulate the others with different units, but molarity is always going to be liters of solution. And this is true for any of our concentration units, but we can always manipulate this equation. So we get the concentration by dividing the moles by the volume, which is just pretty much a rewriting of this guy. We can figure out how many moles we have by taking the concentration and multiplying it by the volume that we're using. And we can calculate a volume that's going to be required by taking the moles that we want and dividing it by the concentration of the solution that we have. The unit that we put on this is just going to be a capital M. A lesser known concentration unit that we might use is something called molality. And molality is the moles of solute divided by the kilograms of solvent. So we're being very specific about the unit that we're doing here. We're doing mass, and it's specifically a kilogram. And it's no longer solution. You have to make sure that you understand that. Now we're going to divide by the kilograms of just the solvent. And the unit for that is a lowercase m. So it would be real easy sometimes to get molarity and molality confused as far as their units. So you always have to be looking for that. The lowercase m, sometimes it'll be like italicized, is molality. The uppercase m is molarity. And finally, another important mole-based concentration unit is the mole fraction. We're going to see this next week when we talk about gases. The symbol for this is a capital Greek letter chi. And basically, it's going to be the mole fraction of whatever component you want, say A, is going to be the moles of A divided by the sum of all the other moles that are in the solution. So you know you're going to add up the moles of A plus the moles of B plus the moles of C, however many components you have, and that's going to make up the denominator. And then we're going to get this mole fraction. Note that we do not multiply this by 100%. It's not a percentage. It's actually like just a decimal fraction. So typically, it is most practical for accuracy's sake to make a stock solution that's more concentrated than the ones that we're actually going to need. This is because when we go to, say, mass out the solute, if we have a larger mass that we're going to weigh out and we make a little bit bigger solution, we're going to get more significant figures from that. So we'll prepare a more concentrated solution, and then we dilute it down by adding more solvent. We take a portion of this out, and then we dilute it with more solvent to produce a less concentrated solution. So in these problems, we start off with the initial concentration and the volume that we dole out of it. And then we have the final concentration that we want to get and the volume that we wind up with after we add more solvent. So our final concentration is always going to be less than our initial concentration during dilution, and our final volume is going to be greater than our initial volume. We're going to take a small portion of this, we're going to dilute it up to a higher volume that's going to have a lower concentration. So a little review here. Dilution is the process of adding solvent to reduce the concentration, and the amount of solute that remains is going to be the same. So whatever solute we take out of this with our little portion is going to be the same amount of solute that gets spread around in the bulk of our final solution. Using the fact that the solute remains the same, we come up with our dilution equation where we have our initial solute is going to equal the final solute, which means that our C1V1, which is the moles that we started off with, or the amount of solute, really, because it could be any concentration unit that we started off with, is going to equal the final solute, which is C2V2. And we saw that back here where we said that the number of moles, for instance, here is equal to the concentration times the volume by rearranging this equation. And again, that could hold for pretty much any concentration unit that we have. So let's take a look at some different example problems for our concentrations when we're doing concentration problems. This one says, what is the mass percentage of 7.1 grams of ammonium chloride in 25 grams of solution? And to calculate this, we're going to take the mass of our solute, we're going to divide it by the mass of solution, we'll multiply that by 100% because it is a percentage, and we see that that is equal to 28%, which we could also write as 28 mass percent to make it clear that this is a mass percentage. And another way that you're going to often see this written is 28 W over W, so that stands for weight over weight percent. In our next example, we're going to ask, what is the mass percentage of a solution prepared by dissolving 3.17 grams of sodium carbonate in 100 grams of water? So in this scenario, we were given the mass of just the solvent, not the mass of solution like in the previous one. So to do this problem, we have to take the mass of our solute, the 3.17 grams, and then we need to divide that by the sum of the mass of the solvent and the mass of the solute. Because we have mass conservation, this together will be the mass of the solution. We multiply that by 100% and do up our math, and we'll see that we get 3.08% sodium carbonate in water. And as we talked about before, we can take these kind of concentration problems and we could ask for any of the variables. So in this one, we're asking, what is the mass of sodium chloride present in 100 grams of a 10 mass percent solution? Okay, so if we have the mass of the solvent, if we multiply that by the mass percent, by the mass percentage of the solution, we're going to get the mass of the solute, because the mass of the solute divided by 100 grams is going to be the mass percentage. We just rearrange this equation here. And we wind up getting 100 grams times 0.10. That is our 10% number, represented not as a percent but as a decimal. We're going to need to do that. And that's going to equal 10 grams of sodium chloride. So now let's take a look at volume percentage. In this example, we're asked what is the volume percentage of a solution made up from 4 liters of ethanol and 6 liters of water. Again, we need to take our solute, so the less abundant of the two components, which in this case is going to be our ethanol, and then we need to divide that by the total volume that we have. So that would be our 6 liters of water plus our 4 liters of ethanol, and we multiply that by 100%. When we do up that math, we get 40%, which we could write again as 40 volume percent, or 40 V divided by V percent, to indicate that this is in fact a volume percentage. In this example, we're going to be asked what is the volume percentage of a solution made from 3.8 milliliters of nicotine diluted to 1 liter of solution. So in this case, we start off with our 3.8 milliliters. That's our solute, because there's less of the nicotine than there is of the final solution. And we're not even really told what the solvent is here, and it honestly doesn't even really matter that much. What does matter is that we match up these two units. So we need either to convert this to liters or to convert this to milliliters before we finish our problem here, so that we wind up getting a cancellation of these two units. That's called a dimensionless quantity. It doesn't have a unit, and that's what we need in order to get our percentage. So in this case, I chose to convert the liters on the bottom here to milliliters. I would now have 3.8 milliliters divided by 1,000 milliliters times 100%. You can see, and I've rewritten that down here. These units then cancel. And when I do my math up, I see that I have 0.38 volume percent solution of nicotine. So now let's talk about mass over volume percent. And I think you're going to see why I have a little bit of an issue with this unit. And so our first question is, what is the mass volume percent of 88 grams of calcium chloride in 720 milliliters of water? So we start off with the mass of our solute. In this case, it's this 88 grams of calcium chloride. And so we add that 88 grams right there. And then we're going to divide it by the 720 milliliters of water. Obviously, we don't get cancellation of this, and we never really can. I can't convert grams to a unit. It's going to cancel with milliliters or vice versa, because these are two different quantities, mass and our volume. And so the question is, which units do I use? And typically we're always going to use grams over milliliters. And this is where, as we talked about, you're going to have this guy, because the density of water is very close to 1, this is going to be close to grams. So this is kind of approximating a mass percentage. But what we haven't done here is add in this 88 grams. And in this case, where we have a significant mass from our calcium chloride, that's going to be a problem. This is actually going to deviate a lot from mass percentage and really not have a ton of physical meaning. But this is how we're going to do these problems. You're going to be given a mass and a volume, and you're going to divide that mass by the volume, multiply it by 100%, and then we get out 12%, or 12 mass over volume percentage. And we can ask the question the other way, obviously. What mass of sodium fluoride is present in a 25 milliliters of a 0.250 mass over volume percent solution? So we're being asked for mass. We're given a volume. We know that this is mass divided by volume. And we need to plug that in down here, but not with the percent symbol. Okay, or as a percentage. So this needs to be a decimal. We need to divide that by 100. As I've said, we're going to do grams over milliliters when we're doing these calculations. We multiply it by the milliliters in the problem, and we get out 0.0625 grams. Now let's take a look at some examples using molarity. The first one is pretty straightforward. It asks, what is the molarity of 0.27 moles of sodium bromide diluted to 400 milliliters of aqueous solution? So the first thing that we need to remember is that our denominator, when we're calculating molarity, has to be in liters. So we can convert that 400 milliliters over to liters, and we're going to see that we have 0.400 liters of solution. We then just take the number of moles that we were given in the problem, divide it by our 0.400 liters of solution, and we can see that we get 0.68 moles per liter, or a 0.68 molar solution. It's also important to note that our molarity calculations can be combined with any other kind of mole problem that we've done so far. So in this problem, it asks, what is the molarity of a 2-liter solution that contains 3.86 grams of sugar? So now we're being given mass, and we need to figure out how many moles of sugar that is. We have to first calculate the molecular weight of sugar. So we have 6 carbons, 12 hydrogens, 6 oxygens, and we add up all the contributions of that. And we see that sugar has a mass of 180.156 AMU. And we know that that unit is the same as grams per mole. We then take the mass that we're given in the problem of sugar, 3.86 grams. We set up our conversion factor here, where we know that now that there's 180.156 grams for every 1 mole of sugar. And when we do those calculations, we get 0.0214 moles of sugar. Now that we know the moles of sugar, all we need to do is take those moles and divide it by the volume of the solution in liters. In this case, there's 2 liters, and we get that there is a 0.0107 molar solution of sugar. Let's take a look at an example of molality and an example for mole fraction. In this first question, it says, what is the molality of a solution prepared by dissolving 1.3 moles of lithium chloride in 1 liter of water? So molality is going to be the number of moles that we have divided by the amount of solvent we have in kilograms. So the first thing we need to do is convert this 1 liter volume to kilograms. We do that by multiplying by the density of water. Water is 1 gram per milliliter, or 1 kilogram per liter. So when we do this math out, we see that 1 liter of water weighs 1 kilogram. We then take the number of moles of lithium chloride, 1.3 moles, divide that by 1 kilogram of water, and we get 1.3 moles per kilogram of solution, or 1.3 molal solution. Now let's take a look at a mass fraction example. So a sample of gas contains 1.2 moles of helium, 3.8 moles of neon, and 7.4 moles of argon. What is the mole fraction of neon in the sample? So here we have an example where we're making a solution that's comprised entirely of gases, but we know that we can do that. That's not a problem. If we look back to our definition of mole fraction, we can see that the mole fraction in neon is going to be the moles of neon we have over the sum of all the other components, all their moles. And when we plug in those values, we get 3.8 moles of neon divided by 1.2 moles plus 3.8 moles plus 7.4 moles. We do all that math up and we'll see that we cancel all of our mole units in this. And we wind up with this dimensionless fraction right here. And mole fraction, as the name implies, should always be a fraction. It will be some value between 0 and 1. And in this case, it comes out to 0.31 mole fraction.